we will hand over the reins to our next speaker, who is Domenico Salvagnin from Padova. Please mute yourself if you haven't been muting. I'll try to mute people.
You
I'm
can
going to
mute
mute
everybody.
everyone. Yeah. I'm trying to mute everyone. There we go. Now,
can you hear me?
Yes, now you're unmuted, and we can see your talk. So the next speaker will be, like I mentioned, Domenico, from Padova, but I think doing some interesting work from his time also together working with the CPLEX team on how CPLEX implemented Bender's decomposition.
That's exactly the topic. So yeah, this is joint work with Pierre Bonabi and Andrea Tramontani from the CPLEX team. And it is about indeed implementing automatic benders within a black box MIP solver. So let me give you first a quick overview about what benders decomposition is. So let's suppose you're given a mixed integer linear program, which has the property that it simplifies significantly once a subset of variables are fixed to some value. And let's say that these variables we call the x variables. The gist of benders is to turn this into an iterative process in which you split the problem in two. So on the one hand, you have a master problem, and the purpose of the master problem is to find a value for those complicating variables, and to find out what the contribution of the other variables is to the objective, the other variables that are not anymore in the master problem, which is what we call the y variables. So you solve the master problem and you get a candidate solution, let's call it x star, and this is effectively a partial solution to your original problem, and you want to see whether this can indeed be completed into a full solution of your problem, and if this is indeed an optimal solution even. And to do that, you solve the other part of the problem, which is the so-called Bender's subproblem, or cut generating LP, or worker, whatever you call it. And this is pretty much just solving the original problem for a fixed choice of the x variables. And the good news is that we do not just satisfy ourselves with a kind of yes/no answer to that, but we use LP duality to get back globally valid information from the solution process of this problem in the form of globally valid cuts that we add back to master, and then we reiterate until we no longer derive, you can no longer derive cuts, and so the solution that we get from master is indeed the optimal one for the original problem. Depending on the status of the cut generating LP, we can derive two different kinds of cuts. The first one is a so-called feasibility cuts. So this is happening when the cut generating LP is infeasible for the given choice of x star. In the other case, when the cut generating LP is feasible, but master is currently underestimating the contribution of the continuous variables to the objective, we derive a so-called optimality cut that makes sure that master has the, let's say, perfect information about eta for the given choice of x star, and also as a valid bound for the remaining choices. Okay, so this is very quickly the main idea behind Bender's decomposition. And when do you want to use Benders? Well, again, when the problem simplifies significantly, once you fix a set of variables, and there are at least two common scenarios that pop up in applications. The first one is when you have some form of block decomposition in the subproblem. So once you fix the x variables, what is left decomposes into independent blocks that can be solved again independently. And this happens, for example, frequently in stochastic optimization applications. But this is not the only case. It can also happen that the problem still is in a single block, but simplifies structurally in a very significant way. And the poster child for this is facility location problems. So we know that for facility location problems, even really the one from by the book, you can come up with formulations which have a tight LP relaxation. And the tightness of the LP relaxation comes from these variable upper bound constraints that link pair of indicator variables that tells whether you should open a facility or not, and the assignment variables that can be relaxed to continuous in most cases. So the LP relaxation is strong, but the sheer number of those variable upper bounds constraints makes the LP solver extremely slow. On the other hand, once the master variables are fixed, those collapse into simple variable bounds, and the simplex solver is extremely effective at dealing with those. So you get this massive simplification just by fixing those master variables to some value. So these are the, I would say, the most common cases in which you would want to use benders. And there are many interesting applications that kind of fall into these two categories. So I already mentioned facility location, but there are also other classes of problems. For example, network design optimization problems most of the times follow this pattern. And of course, we have already cited a stochastic optimization. And the point is that for many of those applications, Bender's decomposition is pretty much the only method that can solve the problem to optimality for instances of realistic size. So this was our main motivation. We wanted to add Bender's decomposition as a tool to the solver toolbox, so that a user could try it out on his problems pretty much by pushing a button without having to implement the whole machinery himself. And for that to work, I mean, a generic automatic Bender's implementation has to follow some criteria. The first one, again, it has to be general purpose. So this is not an implementation which is tailored to a specific class of problems. It has to work on any model which is amenable to Bender's decomposition out of the box. It has to be numerically robust in the sense that at least it should not choke on numerical errors when the when regular branch and cut would have not on a complete model. So we don't want this to be more unreliable than the obvious alternative. And of course, it has to be fast, because otherwise it is not very useful. Okay, so this was our main motivation for this. And we started with what is a basic implementation of Bender's decomposition, but still yet not a naive one. So it has already some bells and whistles. So we start by, I will just give you an overview of this basic implementation. So first of all, upon reading the problem, we construct a decomposition. So either by input from the user, or by just doing some automatic split, putting the integer variables into master and the continuous variables into the sub problem. Then we do pre-solve and heuristics on the complete model. And once that is done, we actually apply the decomposition. So it is at this stage that we create the master problem and the corresponding sub problems. Then we, before going to into an enumerative search, we do a so-called Bender's cut loop, in which we try to warm start the master problem with a good set of cuts. And we do that by solving the LP relaxation of master, again by Bender's decomposition. And finally, we move to the final stage, which is Bender's branch and cut. This is a regular branch and cut of the master problem, which is now solved as an integer program, where we solve Bender's cuts on the fly. As I was saying, this is a basic implementation in many ways, but still not a too simplistic one. So the cut generating LP is formulated in the primal space, which is already quite a difference from to how you already you mostly see it in papers. We do not solve a MIP at every iteration, but we separate Bender's cuts on the fly as lazy constraints, pretty much as you would separate sub-tool elimination constraints for the TSP. We do some steps in the complete space to get benefit from that, like pre-solve. We have this initial Bender's cut loop, And we already have some normalization, in particular, what we call the L1 normalization, to separate feasibility cut. So again, this is maybe not the most advanced thing, but still not too naive. And we were kind of expecting that we could have already seen some good results, at least on models that were amenable to Bander's decomposition. And it turns out that this was by far not the case. So this initial implementation of Bander's on a set of models on which we know Bander's to work was almost 50% slower than regular branch and cut. And it could solve less models, so there were more timeouts within the 10,000 seconds time limit. So this was quite disappointing because, again, this was not on an average testbed. It was on a testbed of problems which are known to be good for Bander's decomposition. So clearly, you need more, much more, to have a state-of-the-art and robust implementation of Bander's. And in the rest of the talk, I will basically try to describe what we had to add on top of this initial implementation to come up with something that actually works. So the advanced techniques that I will describe are as follows. So a generic stabilization procedure for the initial cut loop, a lot of tricks and in order to improve the numerical stability of the method, because again, whenever you have these cutting planes procedures, numerical issues are always behind the corner, and you have to take specific care in the case of Bander's cuts. The special handling of generalized bound constraints, and I will tell what those are in a few minutes. And then the replacement of the initial L1 normalization with a stronger normalization condition. So let me start with the list. So the first bullet point is cut loop stabilization. The purpose for that is to have an improved convergence in the initial Bander's cut loop. And the choice we did in that respect was to use the in-out scheme by Benameur and Neto. This has been proposed a few years ago, and there is already, I would say, a solid computational evidence that this is working quite well with Bander's cuts. So this was kind of the natural choice for us. And in order to work, this method needs a core point, x0, which is a point in the relative interior of the polyhedron defined by the cutting planes that you're separating. And most of the times, if you know the specific application, you can come up with a trivial core point, like 1/2, 1/2, 1/2, and things like that. But our implementation is generic, so we do not have such luxury. So we have to compute the core point explicitly given an arbitrary problem. And the way we do it is we just use solve the LP relaxation of the original problem without objective, with barrier, and with crossover disabled. So as you can clearly see, this does not come from free. So it can be expensive, although most of the times it's not. And it is a small price to pay to have a generic implementation of in-out. And once that is computed, the method is quite simple, I would say. It pretty much does binary search on the segment between x star and x0 until a violated cut is found. And from the theoretical point of view, this has only weak theoretical guarantees. So I guess that the most you can prove is that it will not return a dominated optimality cut. But apart from that, there is not much else that you can prove about it. Still, as I was saying, there is a strong computational evidence that this works, and it has a few side effects. So it was kind of a no-brainer to use, and I will show later what the impact of this is. Numerical stability. Again, here is a long list of small things that we did to improve the numerical behavior of the method. I guess that the less obvious one, at least it was the less obvious for me, is that you need a slightly different definition of cut violation between optimality and feasibility cuts. And I will try to give the intuition behind that. So an optimality cut as a kind of a natural scaling in which the eta variable has a coefficient equal to 1. And if you use this scaling, the cut violation can naturally be interpreted as the amount by which master is underestimating the contribution of the continuous variables to the objective. So for optimality case, you can argue that it is not so difficult to come up with a reasonable tolerance to use. There is no such thing on the other hand for feasibility cuts. Any scaling of a feasibility cut is as arbitrary as any other. So we have to come up with how to scale the cut and how to decide whether it is violated or not. And what we eventually settled for was to decide that a given X star is violated by feasibility cut if and only if the corresponding cut generating LP is infeasible. So this is consistent with what the regular branching cut would have done. And notice that we can decide this before even computing the cut itself. Now, of course, what can happen is that you take this decision, then you compute the cut, and the cut itself is bad from the numerical point of view, and you cannot add it, or it is not violated enough according to reasonable tolerances, and then you have to deal with that. But this is still better than any other alternative that we tried, basically. So this was, at least for me, a non-obvious way to deal with this thing. Then there are other small things. Well, one is quite natural. If you are able to detect that the cut generating LP got into numerical troubles, you can try to resolve from scratch or with a different LP algorithm. If the cut is still in a state that you cannot add it to the LP because let's say its dynamism is too big or it's too dense or whatever, what we can still do is to keep on branching, even though the node is integer, until we get down to a leaf node in the branching boundary. And this helps because once you get to a leaf, I mean, even if you're not able to add the cut, you can still throw away the node without losing correctness of the method. Of course, this is not necessarily effective because this branching is not very intelligent, but still, it allows to continue without erroring out. There is still one case that we cannot properly deal with, and it is the case in which master has continuous variables. In that case, you cannot just get away with just getting to a leaf node. And in that case, if we cannot derive a cut, then we have no choice but to error out. Another thing is the scaling of artificial variables. And this is in inside something also quite natural, but I mean, you have to see it happen before you think about it. So the eta variables, again, sum up the contribution of the continuous variables to the problem. And in many cases, they are completely out of scale with respect to the other variables in master. And so this can create numerical instability in the LP solver. And one way to deal with that, the one that we came up with, is to scale the definition of the eta variables themselves. So instead of setting the eta variables equal to dy, we just set it to dy scaled by some scalar that is decided at the beginning of the solving process. And this is simple, but in many cases it is of great help in reducing the numerical problems of the method. I mean, it helps in making sure that optimality cuts do not have a bad dynamism, and so we can add them to the problem instead of throwing them away. Finally, we extended the cut generating LP to be able to cut array, not just a point. This is a small extension to the cut generating LP logic, and it is needed because in our generic implementation, it did happen that sometimes masters were unbounded, in particular at the beginning of the solving process. And again, it is a small thing that we did not find anywhere else. So it is a small, yet another small contribution to this effort. let me move to the next point, which is the generalized bound constraint. A generalized bound constraint is a constraint which involves only one worker variable. So you can see it as a generalization of the variable bound constraints that we saw for facility location. And well, first of all, it arises in application. So this is not just an empty generalization. It does happen in practice. And of course, you can easily see that those constraints also turn into simple bounds once all master variables are fixed. And this is exactly what we do, because they can have a great effect in speeding up the Bender's CAD generating LP. A word of caution though, there is again a trade-off to be made. The CAD generating LP gets much faster, but the CADs are potentially weaker because those constraints are turned into simple bounds and they are ignored by any normalization condition. So again, there is a trade-off to be made even in this case. So finally, concerning
this is your 5-minute warning.
Yeah, well, I'm almost done.
Perfect.
Finally, regarding the strong normalization. So as I was saying, in order to derive and separate stronger cuts, we use this in-out scheme, but this does not have strong theoretical guarantees. And in theory, you can do better. There is a better normalization that was recently introduced by Conforti and Woolsey that can be used for pretty much any time you separate a cut by solving an LP. And thus, in particular, it works for Benders, for optimality cuts, feasibility cuts, whatever. And this also needs a core point, x0. And the intuition behind it is that by solving a slightly modified CAD generating LP, you find the farthest point on the line segment between x0 and x star. And if you do that and then do some duality as usual, you can prove that this returns a facet of the polyhedron you're interested in with a probability 1, which is pretty much as good as it can get. Unfortunately, this is theoretically very strong, but it does have side effects. So the CAD generating LP gets quite harder to solve. And also in the case of optimality cuts, it gets numerically nasty because the detail is that the objective has to be turned into a constraint of the problem. And yeah, most of the times this is not a good idea. So in practice, it has to be activated with care and not just used blindly. So what we ended up doing in our implementation was to use it only for feasibility cuts, because there the side effects are much smaller. Okay, so this was the end of the long list of things that we added to our implementation, and the overall effect of those was quite significant. So again, our initial implementation was almost 50% slower than regular branch and cut. By adding all of those things, we got to something which is more than 4 times faster than regular branch and cut. So this is, as you can tell, very significant. And maybe even more importantly, we are able to solve more models to optimality. So we really benefit from that in being able to solve problems that would not be able to solve otherwise. And this is the biggest take-home message here, that coming up with a state-of-the-art implementation of Benders is not as trivial as it might sound. So it takes a lot of different techniques in order to have something which is at the same time fast, robust, and generic as a solver, as you would expect from a MIP solver nowadays. And I guess that completes my presentation.
Invite you to unmute. Maybe I'll mute everyone. Are there any questions? Oh, I see a question coming in the chat. There's a couple of questions from the chat. So maybe I will ask a couple of these questions. First one from Jasper. How How do you select, Domenico, how do you select the complicating variables to keep in the master problem? You select all non-applied binary variables, but do you keep some continuous variables under certain conditions? So how do you decide the actual decomposition, I guess? Oh, you're muted. I'm sorry. I muted you. Let me unmute you. Sorry, go ahead.
Can you hear me?
Yeah, now we can. So how do you decide the decomposition?
So automatically, the only thing we can do is to put all integer variables into master and everything else into the sub-problem. You can change that by supplying a user-defined decomposition via annotation. And in that case, of course, we can have continuous variables in master as well.
Okay, thanks.
Thank you.
And then I have a question also here from Robert Hildebrand, which is maybe a lot of people had this question. You kept referring to the dynamism of a cut, and that sounds really great, but somehow you didn't like it if the cut had too much dynamism. So could you explain what dynamism is?
This is the ratio between the absolute value of the largest coefficient and the absolute value of the smallest coefficient. I mean, the non-zeros, of course. And the higher this dynamism, the more numerically challenging and troublesome the cut is when you add it to the LP solver.
See, no other questions. I'm going to ask one other question. Andrea, I was going to ask a question. Did you want to ask a question?
No. Then you go, Jeff. Go.
No. My question was, do you always just have one eta, or do you sometimes, like a stochastic programming, sometimes people like these multi-cut methods? Are there ways to sort of do the Venn aggregation of the Bender's type cuts in a different way?
No. So, well, we have one eta variable for each block.
For each block, you have one eta per block. Okay.
Yes. Okay. Because otherwise, this would hinder the decomposition of the subproblem. Okay, I see questions still. Well, the code available, unfortunately, well, not, because this is a commercial product. So you get it as part of Cplex, which is not open source. How often do you use the strong normalization? Well, if I remember correctly, maybe Andrea or Pierre can correct me. We use the strong normalization. So first of all, we use the normalization anytime we have to separate a feasibility cut. We use non-normalization when we have to separate an optimality cut. And when we have to separate a feasibility cut, I guess that by default, we always use nowadays the strong normalization.
Okay, 2 minutes left. I'll let Andrea ask a question.
So I was wondering, Domenico, which one, is there any one of the ingredients that you discussed about that is making, let's say, I wouldn't say the most of the difference, but that was surprisingly useful?
Well, I can show you a slide that I didn't present. So this is the effect of the individual. I don't know if you can see it.
Yes.
Okay, so this gives the impact of the individual features if you switch them off with respect to our current Bender's default. And what you can see is that, for example, both in-out and the strong normalization are quite important, but they kind of complement each other. So if you switch off only one of the two, the other will compensate to some extent. On the other hand, if you switch them out both, then you get a significant slowdown. So this is I guess those two combined get the biggest effect. And then for me, it was also surprising to see the effect of generalized bound constraints. And here, I guess that the point is those generalized bound constraints do not really appear in any class of problems. I mean, they appear only in some, but on those in which they appear, dealing with them is extremely important, because they can really make the cut generating LP orders of magnitude faster. And this has, of course, a direct effect.
That makes sense, yes.
Okay, well, let's thank the speaker one more time.
Thank you.